the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
PE is a senior principal environmental engineer at Geosyntec. He's based out of Arizona. His primary expertise is in advanced water treatment technologies and characterization.
Hi, Dibs. Can you hear me?
Oh yeah, so you're here. All right, so I was going to introduce Kark and then Kark was going to introduce, but again, since George is here, I'll stop here and basically hand it over to you, George. Folks, my good friend and a senior principal engineer from Geosyntec, George Hollerbeck, is here, and he will introduce all the speakers. Go ahead. George. I think he froze.
Like last time? No, he's moving. He's just trying to figure out where his notes are.
I'm in, I think. Sorry.
All right. Okay, go ahead. Yeah, we can hear you all right.
I'm sorry. I apologize.
No problem.
I think I had the wrong link. So can everyone hear me? Okay.
Yes.
Okay. So thank you very much, Dibs, for another year of the sustainability webinar series. I think Geosyntec's been a member now for the past 4 years. We've been participating actively every semester. We seem to have 1 or 2 speakers. So it's my pleasure. I really like to try to bring in some different talent within the company across the country and from some different offices. And very pleased to have these 3 colleagues presenting on water reuse. First is Tasha Karadi. I hope I didn't mess up your name, Tasha. Tasha is one of our senior engineers out of the Walnut Creek, California office. She's a graduate of Berkeley, University of California, Berkeley, but also she's has a master's in environmental engineering at Stanford, California raised. Then we have Kirk Craig, who's in our Phoenix, Arizona office. Kirk is runs our design center in Phoenix, has a large team in Phoenix, and works on a lot of different water projects. Apologize for the dogs. And then last but not least is Phil Benson. Phil is in our Washington, D.C. office, a graduate of Stanford University. He's a ChemE. But all these professionals that we have speaking today are leaders in our process engineering group and also in our water reuse and water treatment and wastewater treatment group. So I'm pleased to present them. You can go to the next slide. So I did want to talk a little bit about what our topic is going to be today. It's on water reuse programs, and you'll enjoy the 3 of them speaking. They're going to give their perspective. Tasha's going to speak more on the California perspective and the projects that she works on out there. Kirk is going to talk about, obviously, what's going on in the Arizona area and the the arid regions that he lives in. And then Phil, who's a longtime professional, wastewater professional, is going to talk a little bit about the implementation and project delivery of some of these systems. A little bit about Geosyntec. We're right now about 1,800 plus professionals. We have our main practices are ESG, water and wastewater, water and natural resource assessment. I think our bread and butter has always been site assessment and remediation, but we're very much involved in air quality, environmental planning, waste management. And where we got our start really was in geotechnical engineering. So we have a very strong geotechnical program too. So we have over 80 plus offices in the United States, and our international offices are growing. We have a significant presence in the UK and IE, significant presence in Sweden, and Australia, and we actually just started our first office in Spain. So we are growing internationally, and our goal is to is project excellence. We have what I would say is we have it's a unique blend of people. We have over I think 80% of our professionals are advanced degrees, and maybe 20% of our professionals are have PhDs. But we provide highly valued solutions. We work on complex projects, so that's what we're all about. We're not, I wouldn't say we're a commodity provider of engineering services. We work on complex issues, and so that's our strength. Next slide. Next slide. Let's see. I'm still seeing the same slide.
You just advance through this one, Tasha. Just hit advance a bunch of times and we'll walk through those.
There we are. So one of Geosyntec's strengths and beliefs is to have strong university liaisons. This is just a great map showing our current liaisons that we have across the country. We have over 126 relationships at 99 universities. We have 23 advisory board positions. We have 51 cases of joint research publications or projects, and we have supported advanced institutions and provided approximately greater than $4 million in R&D support. And we've leveraged that work in working with different universities. We've leveraged that to over about 20 million in outside R&D funding. So very much universities play a very important role in Geosyntec. As examples, you'll see some of the Canadian locations where we work with University of Waterloo, University of Guelph. A lot of times that's in sediment work, groundwater sampling work, and so we're very much believers in not just carrying out projects, but the research that goes into some of the advanced work. Next slide. Let's see. Can we advance to the next slide? I think we have some. I don't see it right now, Tasha. There we go. So as far as some of our impact of innovation, we approximately have over 250 peer-reviewed publications that we have presented with academia. So, and there are some of the examples, but again, some of the systems that we operate, which are, patented, we have a number of different, research that goes into it, and associated with that, we generally bring in a lot of times academia. So again, a very strong connection with universities and peer-reviewed publications. Next slide. Yeah, it must be my internet, because again, we've got a lot of we have some storms over here, so maybe my internet connection is slow. So I'm seeing the last slide before, but we've gone through the introductions. But I believe there you are. We're looking at the agenda for today. First, Kirk Craig will talk about the Colorado River system and the law of the rivers. And then he'll talk about some of the water reuse regional perspective in Arizona. Tasha's going to give her take on California. And then Phil will close on water minimization, more about the projects that are implemented in the reuse at industrial facilities. And then we'll close out with questions. So with that, I'd like to pass it off to Kirk Craig of our Phoenix, Arizona office. Thanks, Kirk.
All right. Thanks, George. Let me know if you can't hear me. You guys hear me all right? So I'm just going to jump right in. Raise of hands. If there's anybody on this call, click the hands button if you haven't heard about the mega drought in the Southwest. That's probably easier. Anyone? Right? All right, hopefully everybody has, and it's a big deal. And this is a cool little illustration I got. This is from the High Country News, which is this publication up in some little podunk town up in Colorado. Made this illustration back in 1986. Really, it makes you think of the Colorado a little bit differently, especially when you look at the lower left there. And it does not, this great gulf, right, where the mighty Colorado that carved the Grand Canyon now fizzles out before it reaches the Gulf of California. And the reason being is really now we just plummet everywhere. We are diverting and maneuvering and storing every penny, and it's every drop, and that's what's led to this. So I won't really go through all these. It shows how long the Colorado River is. It's really about 1,000 miles less the length of the Mississippi River, and the whole Colorado River Basin is quite a bit smaller than the Mississippi River, but relative to the Mississippi River, like I said, we work this river hard. And I don't know if you guys you talk about acre feet per year. Always when you talk about big volumes of water, we talk in acre feet, right? And 1 acre feet is, I can't remember, I have another slide on, it's like 360,000 gallons. It's enough to supply a family of 5, typical family of 5, water for a year, right? So you can look at this scale, and that number I have highlighted about the volume of the Colorado River is very controversial. Here notice 14 million acre feet, but that number there is what's got us in trouble. So this slide illustrates the little red things are all the diversions. Like we talked about in that last slide, there was little taps that come off the Colorado River, and it's pointed apart. So the red has taken water away from the Colorado River and taken it out to major metropolitan areas, Southern California, LA, San Diego, Phoenix, Tucson, Salt Lake City, Las Vegas, pulling out of the Colorado River. And it's important later because when it comes to water rights, the date at which that new supply line pulled off the Colorado River is what gave them grandfather rights now. So when they go to cutbacks, it goes in reverse order. And it's interesting, you look, if you can see Arizona, where I live, Arizona is the state that has the largest portion of the Colorado River in it, but it has the least grandfathered, has the most junior water right. So even though we share all that, we're going to get cut first compared to California, who tapped into it first and diverted to San Diego. So anyway, a little bit of background. Go ahead, Tasha, the next slide. I won't really talk about these. This is just to really show you how large the Colorado River Basin is, and how many different tribes and cities and power, the amount of habitat associated with it. You know, its GDP, what was on there, puts it as the 12th largest globally if you look at its gross domestic product. Next slide. So, and here's where the problem starts, right? Back in 1922, all the states got together. These states over the right shows you all the states who very much depend on the Colorado River. The amount of water, if you notice on that slide, in that big Colorado River Basin, 90% of the drinking water use comes from the Colorado River in that basin. So, and that's how it's divvied up there on the right. But they did this back in 1922. And back in 1922 was this exceptionally high flow. So everybody, you know, one, there was no even talk of a drought, but they thought that the Colorado River had much more. So remember I said 14 million acre feet? You see, we've got actually 16 million acre feet that's allocated. And the current demand right now is about 15 million acre feet. And just back when they had this, which we'll get to, when they started talking about this back in like 2013, when they did this, they projected that the supply would stay in that blue range and the demand would keep going up. Next slide, Tasha. But, so Lake Mead is the barometer, right? It's the thermostat. It's behind Hoover Dam. There's some quotes here from that are like eye-opening back 4 years ago. I first did this presentation in 2018, and it was titled, "Where Will My Water Come From in 5 years?" And unfortunately, when I first did it, it sped up even then. So the picture on the right shows Lake Mead, and the level on Lake Mead is what they dictate these water cutbacks on. All these states got together and they said, okay, when Lake Mead hits these levels on the left, that's feet above sea level, we'll trigger these shortages. And you look historically from 1939 to 2003, it was all great, that top yellow line. And then things start turning bad. And the picture on the right, those things that look like towers, those are where the big turbines are, where the hydroelectric energy for where, you know, thousands and thousands of residents, tens of thousands, hundreds of thousands actually get power from this dam. And we're getting close. When you get to the tier 3 shortage, we're approaching the intakes of that, right? So next slide, Tasha. Oh, and Deadpool, by the way, it was the very bottom. That's where they consider the lake empty. So next slide. Give you the idea of, now we get into some projections. So back up a little. One click, easy click. There, up, one more. Forward. That slide, tap it once. Should be a, oh well. Anyway, underneath this, there's another picture. It shows a bunch of politicians, governors who all got together and they were holding hands in 2018, and they got together and they said, okay, when we hit those trigger levels that we saw on that last slide, yeah, we're all going to start cutting back. Well, we hit them, as you saw. We're in tier 2 now. And when they all shook hands, it didn't really happen. So now people are backing out. And now go to the next slide, Tasha. This is the news now. So that's the news from today. There, pull that off. So now look at Lake Mead. So now we're fast forwarding to 2022. And I had that line, and you can just kind of see trajectory, the average elevation of Lake Mead. And remember, the deficit is just being pulled from Lake Mead. Now, over the last few years, Colorado River Basin is producing about 12 million acre feet. So when you look at a million acre feet, that's 320 billion gallons, right? That's a million households of 5 for a year. And we're taking that where we're actually a deficit of something, you know, on the order of 4 million. So there's a big deficit and a big problem that's happening in a great portion of the United States. And now you guys can kind of see the framework and the history and how we screwed up way back in 1922 when we didn't even have any foresight of the draw and the growth and climate change and things like that. Next slide, Tasha. So what this means for me personally, and this is what's happening. So now we're going to have to really take advantage of every dime. It's been interesting being in Arizona and going to California and seeing these signs about don't use water, we're getting rid of grass. And Colorado, they've had water restrictions. Arizona, Wild West, we just said, hey, until we see it really affect us, we're not going to do anything. And now we're trying to catch up. Now, one of the things the Arizona Department of Environmental Quality is doing, along with agencies in some other states, is direct potable reuse. And that is really where they're going to take effluent from a wastewater treatment plant and go right into a drinking water plant, right? Maybe everybody gets a little bit of a shock factor, but we'll get into reasons why, how that might just be common, where we don't even think twice about that later. So next slide, Tasha. So Arizona, a little bit, I told you how much we get. We get of that, here's the percentage. You know, the Colorado River also supplies a ton of agriculture. And one thing Arizona, or we've been bragging about, it's like, well, hey, we don't use more water than we did in 1970, but we're like twice or three times or whatever the population. So they brag about that, but it's really just because we're phasing out agriculture. We're breaking even. Industry's growing out here. So I think that's kind of a weak argument for us. And here's the distribution. See how low reclaimed water is? Right now, we use this water and we just let it go. Let it go back out. We don't necessarily capture it all. So that really needs to grow. And that's what my office is going to help work on. So next slide. So here's what the breakdown is. To give you an idea, just quickly, when I talk about the reliance on the Colorado River, so the city of Phoenix is 90%, 98% reliant on surface water. So that water all goes into that component where now Arizona is expected to cut back, you know, the equivalent of hundreds of thousands of, you know, or actually millions of households, right, worth of water. So now what Phoenix is doing is they're turning on the pumps in the ground. They're shifting aft. They're taking away their Colorado River and they're starting to pump from the ground. Scottsdale, same thing. They're a little less reliant on surface water, and some of these cities are actually taking water from tributaries that feed the Colorado River. But Scottsdale is cool, and I'll talk about a little bit more. They have a 20 million gallon per day wastewater treatment plant that's got a contract with 22 golf courses, which does help me feel a little bit better about living in like the golf course capital of the world here in the middle of the Sonoran Desert. And that may change, right? We may see that forced over the next 5 years. But they also are the first agency in Colorado to get a direct potable reuse license. And we're helping redo that program, which I'll talk about. And the other ones, Goodyear's 100% groundwater, et cetera. The different, Tucson's interesting. Tucson says 100% groundwater, but really they do what's on the next slide. So I'll show you. Here, remember, Tucson says they use 100% groundwater, but what they do is interesting. Tasha, next slide. The way we reuse water here, and remember, this is important because now that we have to come up with these, millions and millions of gallons, we waste millions of gallons to our wastewater treatment plant. And there's three ways that you can reuse it, what you call indirect reuse. And that's what Tucson does. They inject all their wastewater effluent, or they re-infiltrate it into the ground, and then they pump it out of the ground, say a few thousand feet down gradient, or a few miles down gradient. And they use the ground as the final buffer. You could use a river, you could use a lake. So that's indirect. And then there's direct supply. And here you see it's coming right out of a wastewater treatment plant. And like I said, Geosyntec just got the contract to help ADQ write their rules and regulations for that, their program. And then there's unplanned de facto, which is kind of what happens now. You discharge into a basin, a river, whatever, and eventually that water gets reused for drinking water. You know, I'd like to say we're all drinking dinosaur pee probably right now because there's a water cycle. So next slide. Here's some examples about what we're doing. Groundwater is deep here. So in Arizona, we push it back into the ground, either with injection wells, and that's called an aquifer storage and recovery well on the left, where we're actually taking wells that do thousands of gallons per minute sometimes, and we push the water back out into the aquifer that we can pull out later because it moves slowly in the subsurface, or we'll let it re-infiltrate. So next slide, Tasha. And go ahead and click on that left picture if you can. I'll just play it while I talk. That's a big reinfiltration. Hopefully it's playing on your end, that a water utility does. And this is a really, really large structure. And they'll allow, what does it say, 350 billions of gallons of water. So what Arizona has been sneakily doing is they've been saying, hey, for years, we're not using our allocation of the Colorado River water, but we're going to divert it and let it infiltrate into the ground and store it for later. And the figure on the right shows elevation changes, where in Tucson, they've been doing this. And I think like green is neutral, and places that are purple is where it's been drawn down, and orange has been mounded. So they mound actually the groundwater and will store it later and reinfiltrate it and bank it. So that's indirect recharge. And we've been doing that in Arizona since the 80s. Next slide, Tasha. So there's purple pipe you'll hear about, and Tucson was big on this, where they actually take effluent. You're talking, 40 million gallon per day type plants, and taking effluent from that and spreading it around, and instead of wasting it and just letting it go into rivers, using it as influent. And Phil will get into this more, or where they go right into industries and they have purple pipe that says, hey, this is not potable. They take great lengths to keep things separate. So there's no way from a public perception, things are physically separate, that we can get our wastewater effluent mixed with our drinking water. And then they also use it to make restoration projects. So here, this is where an area where the river was dry because it got diverted is now moved back into play, and some endangered species and things are finding refuge there. Next slide, Tasha. So direct potable reuse. I told you that Geosyntec got this contract. We're super excited about it. We're going to help them write their direct potable reuse program over the next 2 years. And the reason why we're really well suited for this is because you do a process to get wastewater, municipal wastewater, to where we can discharge it into the environment. And then then we take clean water from the ground and we make it into drinking water. But in order to get from effluent to drinking water, it takes it very advanced processes. And Geosyntec is used to that because we treat industrial wastewater a lot. And industrial wastewater's got cocktails of really crazy and fun, from my perspective, stuff. So it's all these technologies you see listed there: reverse osmosis, advanced oxidation, et cetera, that bridges that gap. So I think that's why Arizona likes us, why we're really excited about this big trend to use direct discharge once the public gets as used to it as indirect potable reuse, the direct potable reuse. So with that, I think we're want to make sure we have enough time. So I will turn it over to Tasha, and she'll shift over to California and give you a perspective there.
Thanks, Kirk. Yeah, so I'm going to talk about a regional perspective from California. The challenge in California is similar to what Kirk was describing for Arizona. But here we have the majority of our urban population is not really exactly where we have the majority of our precipitation. And we also don't have enough supply within the state to meet our demands. 70% of California's precipitation falls as snow in the northern part of the state during the winter. And then 75% though of our need is in the lower 2/3 of the state. So we've had a number of major infrastructure projects across the state, aqueducts, dams, and reservoirs. And like Kirk was saying, we do get quite a bit of our supply from the Colorado River. So Los Angeles alone actually imports 50% of their water from the LA Aqueduct, the Colorado River Aqueduct, and also from the state water project. So those 3 aqueducts alone, that's more than 1,300 miles in length. And that's actually just even greater than the length of California itself, which is 900 miles. So combine that now with our drought conditions, like Kirk was talking about. The last 20 years have been the driest we've experienced in California for over 1,000 years. And our reservoirs across the state are at about 41% of the capacity compared to our historical average of 60%. And as Kirk has discussed, there's continuing restrictions on water usage from the Colorado River due to these drought conditions. And 40% of our drinking water supply comes from groundwater, and our reliance on groundwater has resulted in overdraft and unsustainable groundwater usage in many of the basins. So with all that said, water is a vital resource, and management of our water supplies and conservation has become increasingly crucial. These are just a few headlines from the past couple days highlighting the discussions around water supply and drought conditions. You can see even being famous won't get you out of your part to conserve. So just looking at the early stages then of water reuse. So is as one component of the solution to California's water issues. Water reuse is not a new concept in that solution. So the first discussions around water use actually go back to the 1950s, 1960s, when water demands were increasing in Southern California due to residential development and a little amusement park that we have in Anaheim. And we started getting seawater intrusion that started to occur at our coast and the drinking water wells in Orange County. So to solve this, Orange County Water District partnered with the Orange County Sanitation District, and they built Water Factory 21 to treat the wastewater and inject it into a barrier to prevent seawater intrusion into the aquifer. On this slide, you can see a photo of the treatment facility from the 1980s, and then also a treatment process flow diagram and the location of the injection wells. And actually, this is part of the brochures that were distributed to the public when they were first rolling this out and getting public buy-in on the project. The project was very fundamental to California's reuse story. In the 1990s, the Water District and the Sanitation District started on a new endeavor to treat wastewater and inject it and recharge a drinking water aquifer, so indirect potable reuse. And that became the groundwater replenishment system. So that brings us to the first example highlighting indirect potable reuse. This project was first discussed in the 1990s and became operational in 2008. And this system takes wastewater that would otherwise go to the Pacific Ocean and treats it and produces high quality water that meets all the state and federal standards. So it supplies 100 million gallons per day, and it has produced over 375 billion gallons of water. There have been a number of benefits to the system, including reducing our dependency on the Colorado River. So this treatment system has a number of advanced treatment processes. You can see the filtration here, RO, and also UV before it goes into the injection wells. And this system actually has supplied 35% of the recharge in the Orange County Basin. That's then extracted for drinking water. So this next example I want to discuss is the use of groundwater that's been impacted with contaminants for direct potable reuse. So we have 515 basins that provide 40% of our water supply in the state. In some areas actually even rely on groundwater as 100% for their supply. In 1997, the Division of Drinking Water for the State Resource Control Board developed this policy memo 97005 to provide guidance for direct potable use of extremely impaired sources. So this memo outlines the process, how to use a contaminated source and assess if it's viable for treatment to use as a drinking water source. So this policy, it walks through all the different steps that are needed to characterize the aquifer, look at the different compounds that may be there, and assess the type of treatment that may be needed. As you can imagine, the requirements of treatment of these contaminated groundwater sources can be quite complex, given the concentrations and complexity of the contaminant mix. So just walking through an example of the type of treatment processes that would be needed. So first, groundwater is extracted and then conveyed to a treatment plant. You'll typically have a liquid granulated activated carbon vessels to remove volatile organic compounds, which are absorbed to the carbon media. And then ion exchange is used for compounds like to remove compounds like perchlorate. And these vessels can be designed to have media that will target specific compounds to remove them. Then there's advanced ultraviolet oxidation reactors, and those can remove compounds like 1,4-dioxane and other volatile organic compounds that don't absorb well to carbon media in that earlier stage of the treatment process. Following that, reverse osmosis will remove other inorganics. And so reverse osmosis, that can remove things like total dissolved solids and then other compounds like hexavalent chromium, selenium, and nitrate. This is certainly a complex and challenging process to implement direct potable reuse of contaminated groundwater. Some of these challenges include just the evolution of drinking water standards, new and emerging contaminants that are identified, advances in technological or toxicological research, advances in the technology to actually detect these compounds, which ultimately can result in a lower screening level for these compounds and detect lower concentrations. It's also a very complex regulatory environment, and also public perception is really crucial to have a project move forward. So it's really imperative to have the public acceptance and involvement during the decision-making process. So with that, I will turn it over to Phil.
Thank you, Tasha. So as Kirk mentioned, a lot of the technologies that we're looking at for water reuse have emerged out of the industrial marketplace. And industry has really had an interesting relationship with the whole water cycle with water reuse. In some cases, industry is the last group to get a water allocation. You've got water for people, you've got water for agriculture, and water for industry. And sometimes industry comes in last in that pecking order. And so companies have had, by necessity, to start to figure out how to do more with less, how to be able to operate and continue their production despite an inconsistent water supply. In addition, industry has really been a leader in water reuse due to sustainability initiatives, due to shareholder demands, customer demands, especially in what I call the water for the business for people industries, companies that sell directly to people. And their customers expect a high level of environmental sustainability, and that translates into a significant look at how to use water better and how to reuse water. Next slide, Tasha. So this is an example of some of the water sustainability goals that are publicly available by major U.S. and international companies. A lot of them are watershed based. They talk about their place within the water universe, within the water environment. They talk about replenishing all of the water that they use in their production. In many cases, doing that by 2030. A lot of these goals were written around the 2020 timeframe and before, and 2030 was kind of a magic year. You'll see a lot of, we'll get this done by 2030. As Kirk said earlier, 2030 is coming really quickly, and maybe even quicker than we anticipated, given how quickly conditions are changing. And so water is becoming a real significant issue for a lot of companies. You can see an example here from Microsoft, become water positive by 2030. And looking at how do they create and put more water back into the environment than they utilize. One of the things that Microsoft is doing is partnering with municipalities and using municipal effluent as their feed source to some of their facilities. And you're seeing that happen at several of their facilities. You're also seeing companies look at really speaking to reuse directly. The L'Oreal example, but in 2030, 100% of the water used in our industrial processes will be recycled or reused in a loop. That commitment to really looking at water use and looking at the place in the water environment and how do you make that better, both in order to have a sustainable and resilient operation where you can continue to operate as things change, but also to have a reputation for being a good environmental steward. Next slide. So when we look at water use and how water is used in industry, and obviously this constitutes a really diverse set of of facilities, depending on what market you're in. A lot of industries have, use cooling water. And so cooling becomes a big target. How do you reduce the amount of water that you use for cooling operations? How do you use different quality sources for cooling operations? Another big user for water is air pollution control. Scrubbers and other technologies to really prevent discharges to the atmosphere. Dust control at certain facilities is another big issue with power plants, facilities that have ash, cement manufacturers have major dust control issues and use a lot of water for dust control. The whole air handling and climate control piece generates and uses a lot of water, as well as irrigation and beautification. And we talk a lot about how does irrigation fit into the whole water balance and what makes sense in terms of going to irrigation techniques that or landscaping techniques that don't require water to reduce water use, or even in some cases looking at irrigation as a positive discharge point for lesser quality water and part of a water reuse strategy. A big thing in industrial production is cleaning systems, product cleaning systems, cleaning in place, either bottle washing and container washing for storing materials, whole plating lines of tanks and rinse tanks, and how is that managed? Transport water, moving product around, whether it's tomatoes in this example or in large mines, you may use water to sluice slurries as part of the mineral processing work. And then there's the human consumption of water, cafeterias, wash water, showers, etc. Next slide. So when you look at water, water reuse, a big part of it is actually, how do you minimize water use? How do you actually get, optimize water use? And then how do you go about looking at that water and what can be reused? So, correcting leaks, preventing unintended losses from the system, really looking at rinsing and cleaning and what do you need? As you go into facilities, you find a lot of places where they do things because they've always done them, not because they need to do them for product quality. So, what is the quality of the product that's required? And are they actually over rinsing, over cleaning to get that quality? Cooling water can be an art. There's still facilities that use once through cooling, and so obviously cooling towers offer an opportunity to reduce that pretty readily. But then even when you have a closed cycle, a cooling tower system, how do you optimize cycles of concentration to manage the water chemistry? Again, that can be an art as much of a science. Looking at water use and product formulation, and then indirectly, what's the water balance for energy production? And then as Kurt talked about earlier, are there sources of water available to you that meet your quality requirements that are not fresh water, that are not potable water sources, that aren't taken away from other parts of the environment? An example of a purple pipe system close to Washington, D.C. is Loudoun County, Virginia. Loudoun County is the data center, the data capital of the United States in a lot of ways. And a couple of reasons for that. One is that when the whole data industry was first evolving, the first big player there was America Online, and they were based in Loudoun County, Virginia. So they built the data highways, the pathways by which data is moved around, that infrastructure for data transport. But the other thing that happened is that Loudoun County developed a purple pipe system where they carved out some of their municipal effluent, treated it to a higher standard, and actually put it back into the distribution network in a purple pipe, where to be a cheap source of cooling water for cooling intensive facilities like data centers. And so it really was an incentive for those facilities to build in Loudoun County, and now it's known as the data capital of the US. Next slide. The other thing you look at is reuse within an industrial facility, and there's really two types of reuse. There's internal reuse to the facility, and that's cascading uses, using effluent from one process as influent to another. One example is countercurrent rinsing, where if you look at large plating shops and there's still a significant industry, especially with heavy industry, with the defense industry. You see a lot of really complex plating operations, you would normally have a concentrated bath followed by a series of rinses to get product quality. Well, in the past, those rinses were largely once through. Each tank had a source of fresh water, and as it became contaminated, it would discharge that contaminated water to some sort of treatment facility. Now what they do is they cascade the tank, so where the clean water comes into the cleanest tank, and it cascades from tank to tank to tank to tank, getting sequentially more contaminated, and then discharges from the most contaminated tank. And they find that reduces their water use a significant amount. And then what you're really starting to see more and more of is almost this water bartering, using treated effluent from one facility as influent for another facility. You're seeing that between different industries. You're seeing that between industry and ag, where industry is working with large agricultural entities to actually take their water that they've treated and is good enough for irrigation for agricultural production. And you're seeing treated municipal effluent streams being used as industrial feedstock as opposed to fresh water. And you get that within the plant environment itself, where you might look at in a really water-starved area, can you actually treat your plant effluent to a level of reuse? Tasha and I are working on a project right now in Mexico where the client's planning on putting a reverse osmosis system in to treat groundwater for their plant use. Well, after they generate wastewater through their production processes, the quality of that wastewater isn't that different from the quality of the water that's going into the RO plant as fresh water. And so we're actually going to blend that into the freshwater stream and to the maximum extent possible, reuse that effluent as influent to the production facility. And then when you look at, and we're going to talk a little bit about the auditing process and how do you prepare a facility for a water reuse project. But you have an increasing risk depending on, obviously the lowest risk is when the water does not contact the product. You have more flexible water quality requirements when there's no contact between the water stream and the product that you're making. And obviously when there's direct contact, there's increasing risk that you're going to impact the product, and folks get a little more sensitive about water quality and a little more making sure that what you're doing isn't going to impact the quality of their final product. Next slide. So when you look at, and I'm going to try to pick up the pace a little bit just to make sure we have time for questions and answers. When you look at some of the things that you have to consider for reuse, there are different kinds of parameters than you might consider for treatment and discharge. You have to look at things that could cause fouling and plugging, iron, silica, suspended solids, things that could cause microbial fouling, BOD, the food sources for organic growth, nutrients for organic growth, even pathogens. I mean, there have been instances of Legionnaire's disease, for example, in cooling water systems that weren't well managed. Next slide. You need to look at compounds that could cause scale under certain circumstances, especially as temperature changes. You may get changes in the ability of something to scale. And if it starts scaling where you don't want it to scale, it could muck up your reuse system. On the opposite side, you also need to pay attention to, are you potentially causing corrosion? Are you gonna deteriorate some of your plant infrastructure because your water is becoming more aggressive and it's becoming more corrosive and is impacting your metal conveyance materials? Next slide. So when you look at implementing a water reuse and recycling project, the first, and in a lot of ways I call this the most important step, is really doing a comprehensive water audit. Understand what you're doing today. You'd be amazed as you get into older facilities, even newer facilities that are worried about production, worried about making a profit. They don't necessarily know how they're using water and really understand all the water sinks, all the water sources, all the things that are contributing to the amount of water they're using. They may have leaks that haven't been identified, and a lot of times these audits will show that this pipe's been leaking for years, and no one knew it, and it's just been leaking to groundwater, and they've been using more water than they expected to use. Really looking at your processes and integrating them throughout the facility. What's the water use of each process? What's the water quality requirements of that process? what kind of water is discharged from that process, and how does it link together in an overall facility balance? And in that kind of roadmap then gives you a list of your choices. What are your options for reuse? What treatment is needed to successfully reuse? What are those things? What do those treatment options cost? How do you validate their effectiveness? And how do you make sure that you continue to be within compliance of your permit conditions? Next slide. So this is kind of a typical roadmap of an operating facility. You can see you've got three major kinds of users. You've got process users where really you're using water to generate the product. And you may have losses associated with that. You may pick up contaminants from that. You've got cooling, and most facilities have some sort of cooling process needed. A lot of cases that's evaporative, so you'll have a water loss through evaporation. And then you'll have a water for people, a sanitary need. Those will be combined with some sort of storage, to enable your water supply to be more reliable. And obviously, at the end of the process, you'll have to have some sort of treatment and ultimately discharge that water from your facility, either back to the environment or into a sewer system. Next slide. And so a couple of case studies to kind of demonstrate how we go about doing this. So this is a project we did for a pharmaceutical manufacturing facility in Arizona. And the stars really indicate the things we changed. So when we started this project, you had a city water source that was used for all the water in the plant. About 40% of it was used directly for the product and the production lines, either product formulation or cleaning in place or equipment wash down. About 25% was used for cooling, 25% for sanitary and other miscellaneous uses, and 10% for landscaping. And so this client was driven by corporate level sustainability goals. They wanted to look towards, could they get closer to zero discharge? They were looking at their costs and could they reduce costs? And they were looking at managing risks of water interruptions and being prepared for that. So what we did is in a number of strategic locations, we increased storage to give them more resiliency. We converted to a different landscaping strategy to eliminate that 10% irrigation feed. And if you look at the flow diagram up in this part of it, we took water that was treated and previously had been discharged to a POTW and recirculated it for cooling, thus reducing the amount of water used by about 35% for the facility. Next slide. And so a few challenges. It was a complex flow diagram. The cooling tower water demand fluctuated, which is why we put increased storage in place to really allow cooling to accommodate reuse for 90% of the year. And we changed the irrigation out because it was a large water sink. Go ahead to the next slide. I'm gonna try to wrap up with a second example. This is a cement plant water management strategy where you see water is used, and water is actually produced at the quarry by precipitation. It's used in crushing and aggregate washing. It's also used extensively for dust control. So in this project, what we did was try to improve both the dust control and tire washing operations to kind of normalize the amount of water that was used. We, instead of discharging treated wastewater from the wastewater treatment plant, we reused that for some of the dust control operations, thereby reducing the amount of city water that we required. And we also used some of the precipitation, the quarry water that comes from rainfall, and captured that and input that into the dust control systems, thereby reducing the amount of city water used. So trying to reuse water of adequate quality, into the operations that are needed to successfully operate the plant. Go ahead on the next slide. And so a couple of challenges here. It was a complex water system with really a not well-defined pumping operation. So we, through metering pumps and looking at how things ran, were really able to kind of rationalize their pumping strategy. The tire wash wasted a lot of water and discharged water that didn't need to be wasted. And so we adjusted how they did tire washing. We changed the nozzles and changed the operation to eliminate that wasted runoff. And then we optimized storage in ponds and tanks so that there was always enough reused water available in order to supply the dust control and tire washing operations that were needed. And I'm going to finish up with one last slide. And it's just kind of just for kicks. Go to the next slide, Tasha. This is a project we did several years ago for a tuna processor. This was actually driven by compliance and by a wastewater plant that was overloaded. And so one of the things we did, and this gets to the value of that water footprinting, we were able to isolate high strength wastes, really high strength, high pollutant wastes, which were the red bubbles, from the high flow, low pollutant streams, which are the green bubbles, and pull those streams out of the treatment plant, thereby allowing the plant to operate better, and also giving us the opportunity to look at those streams as reuse candidates, since they were producing a low strength material that could be used in other processes without negatively impacting them. I know I'm getting right on the deadline, so let me, I'll stop here. And just closing events, go 2 slides, Tasha, real quick. One of the things in closing, just you're seeing a real increase in what I call the one water mentality. Looking at water as one integrated product that impacts everything we do, whether it's rain and storm water, surface water, groundwater, recycled water, drinking water, or wastewater, and really looking at the combined value of that asset across all those subcategories, and how can you optimize the use of that water for society's benefit. And you're seeing that within the consulting community, you're seeing that within what our customers are asking us for, and you're increasingly seeing that within the regulatory community and how they apply the regulatory framework to users of water. Thank you.
Hey, that was a very interesting presentation. I'm glad that we finished right on time.